So today we are going to talk about the direct reduced iron or DRI, especially in context of hydrogen based production. We will discuss two key parameters. One is Fe and other is metallization. In DRI, a higher total Fe means more iron is available per pellet. This is very obvious point known to everyone. However, it's important to understand that not all of this iron is converted to its metallic form. Some of it remain as a iron oxide, and this leftover iron oxide need to be reduced later in the electric arc furnace using additional reductant and such as carbon. So the our primary challenge we face with the DRI is low metallization. When metallization is low, the DRI contain less metallic Fe and more FeO. And this forces the electric arc furnace to expend more energy and use more reductant like carbon to recover the iron from the FeO. As a direct consequences, this increases operational cost and also raises CO2 emission during the EF phase of steel making. Now, here is a comparison chart where we can see that if we produce DRI with a high total Fe for the same degree of metallization, there will actually be more FeO left in the DRI. So this happens because a higher total Fe content provide a larger base for FeO to remain in proportion. So let's look at an example comparing two DRI scenario that for 1 ton of feedstock. In both cases, we will assume that metallization is 95%, which means that the Fe content is 5% of the total Fe. As we can see that from the comparison, the DRI with the higher Fe content end up with a more FeO. Higher Fe content end up with the more FeO, and 144 versus 135, that is concluded in the last column, even though it also has a more metallic Fe that is already shown in the calculation sheet. So the main takeaway from these is that the producing DRI with a high metallization as close to 100% as possible is more beneficial than simply increasing total Fe. The reason for this is that high metallization minimizes the FeO content, which in turn reduces the burden on electric arc furnace. Now, a practical comparison is also shown by case A and case B. And now, in these two specific cases, case A contain 100 kg of DRI with 90% total Fe and 90% metallization. Case B contain 100% of DRI with a 90 higher, that is 96% total Fe, but still has got the same 90% metallization. So, first let us calculate how much of the iron in each case is metallic or pure Fe. In case of the metallic Fe is the total Fe multiplied by the metallization, which is 90 times 0.9 give 81 kg. In case B, the metallic Fe is 96 times 0.9, which equals 86.4 kg. So we can say that another one phase is left in our calculation, which is about the iron which is left as FeO. So this is the unreduced iron, which is 10% of the total Fe, since metallization is 90%. So in case A, the FeO is the total Fe, that is 90 kg multiplied by the unreduced fraction 0.1, which equals 9 kg of FeO. In case B, FeO is the total Fe 96 multiplied by unreduced fraction 0.1, which results 9.6. So what does this mean for the EF? The EF has to recover the iron from these FeO. EF has to recover the iron from this FeO by reducing it with carbon and other reductant. So in case A, if we look into, the EF has to process 9 kg of FeO, and in case B, EF has to produce 9.6 kg of FeO. So even though case B has a more total Fe, it end up with creating more FeO for EF to handle, because the metallization level was same in both scenario. So the final lesson from the comparison is that if the metallization were higher, for example 95% instead of 90%, both cases would have much less FeO left over. Therefore, aiming for higher metallization as close to 100% as possible is what truly reduces the FeO and make the EAF job easier, regardless of the total Fe content. So it create a lot of clarity on our Fe percent and FeO. So, a major consequences of high FeO in the DRI is an increased demand of reductant in EAF that we have already discussed. This is because the FeO must be reduced to metallic Fe, a process that requires a carbon source like coke or graphite. So, the chemical reaction for that is the FeO plus C will be Fe plus CO. So, the consequences is that the more carbon is consumed and which increases the operational cost, and higher carbon uses lead to increased carbon monoxide and carbon dioxide emission, reducing the sustainability of the steel production. So now coming to the another consequences of the higher energy consumption is that the reason is about this FeO, and which is basically endothermic reaction, and it means that we need a lot of heat. So the EF must supply the additional energy to complete the reaction. So consequences are twofold. First, increase the power consumption, drives up production cost, and second, it leads to a longer tap to tap time, which reduces the overall productivity of the furnace. Now coming to this higher FeO and its consequences, so we can see that high FeO also lead to a reduced metallic yield. This happens because if the FeO is not fully reduced in the EAF, some of the iron remains trapped in the slag, which result in loss of iron unit. The direct consequences is a lower metallic yield, meaning less steel is produced. So productivity also goes down. To compensate for these iron losses, additional raw material may be needed, which further increases the cost of production also. Now coming to the our next slide, which is about this uh, high FeO and its consequences on the slag. So because of this FeO react with the other element in EF such as a lime to form a Fe containing slag, the consequences are the first excessive slag volume, which complicate the handling and disposal of slag, and second is that the slag forming issue, as if you affect the viscosity of the slag, which can reduce heat transfer and furnace efficiency also. So and other consequences are also is there is about a refractory wear, and we can see that the high FeO content also causes increased wear on the EF refractory lining. The reason for this is that the FeO is highly reactive compound that aggressively attack the refractory lining. The consequences of this is accelerated refractory wear, which increase the frequency and cost of maintenance and a reduced furnace lifespan, and which can lead to more cost and unplanned downtime also, because we do not know if our decay of the refractory on a faster mode, there are development of more hotspots, and if those hotspots cannot be taken care properly, then we that gets converted into a bigger shutdown. Similarly, coming to the process instability, so high FeO level also lead to a process instability in EAF, and this happens because high FeO affect the chemical balance of the furnace, which can lead to the unpredictable reaction and slag properties. The consequences are operational inefficiencies and difficulty in maintaining the process control. So these increases the risk of furnace delays and quality issues, many quality issues in the final steel product. So let's quantify the impact, which is very important, and so it is already very clearly shown to sensitize the team that regarding carbon demand for every 1 kg of FeO, approximately 0.27 kg of carbon is consumed. And for energy consumption, the reduction of FeO consume about 1.5 kilowatt hour of energy per kg of FeO. So you can imagine that how this FeO consume, can just swing the both factor towards the adverse side. And for the loss of metallic yield, if the FeO goes into the slag, the iron loss, which is about 70% of the FeO weight. So this is a big loss. So coming to our next slide, which is about the energy that we have already, metallic losses also we have discussed, and we also come across the most important part is the environmental impact. And we can say that if we have already we have shown that with the presence of FeO, our consumption of fuel is also increasing, slag is increasing, operational cost is also increasing, productivity comes down, refractory has a lot of wear and tear, and cost of production goes up, productivity goes down. So this all nothing is going to be good towards achieving a betterment of the parameters towards the benchmark data. So we can say that the reaction using the carbon emit around 1.57 kg of CO2 for every kg of FeO reduced, that we have seen. This means that low metallization DRI produce twice the CO2 emission. This already there is a very sensible table is showing, and which undermine also the green steel initiative. So in conclusion, high metallization DRI is a win-win solution for the operator, management and sustainability effort. It saves energy, reduces cost, and align perfectly with the green steel goals.